some of the objects that I would like to tell you about have already featured in some of the earlier talks. So Matti talked a little bit about nonlinear waves. There are going to be nonlinear waves here coming in a second. But a little bit more surprising for me is the fact that even gauges and parallel transport have already featured, which are going to be two very important players in what I have to say. So the talk is really about the following. So I would like to put you first in the right kind of frame of mind. It's about the following. So whenever you have waves, let's just, we will be quite precise about the type of waves that we are going to be looking at later on. But whenever you have waves, sometimes the waves are determined by a geometric object. So for example, you can think about Einstein manifolds, where you could have the metric being, the waves being space-time itself in some sense. The example that we're going to see in a minute has to do with other geometric structure, but these geometric structures in some sense determine the form of the wave equation. And the problem that you want to face is the following. You have an observer that is actually making local measurements, yeah? And then the observer is actually very clever, as we're going to see, and produces some waves. These waves sort of go away and then come back, and then you measure when they come back. And from those measurements, essentially, you want to reconstruct the geometric object. Yeah? So that's essentially the context of the next phrase. And as I said, the geometric structures could be many things somehow, as we've seen actually in Matti's talk, was the actual Lorentzian metric. But in our case, in my case, in this talk today, is going to be a connection, which is an object that I'm going to try to sort of explain what it is in very simple terms. Okay, so now in this talk, the background is going to be very easy and it's going to be fixed, and it's just simply going to be the usual R4 with the Minkowski metric. Yeah, just the standard R1 plus 3 from special relativity. And here is the thing that I'd like to tell you about what a connection is for our purposes. So you can define this in all sorts of different ways. You can talk about bundles and so on, but for the purposes of this talk, none of that is really necessary. So a connection for us is going to be essentially 4 matrices. Yeah? So if you know the language of one forms, that's essentially a matrix of one forms, but you can write them out in this very sort of simple form. A0 dt plus A1 dx1 plus A2 dx2 plus A3 dx3. And each one is a matrix, but the matrix takes values in the skew Hermitian matrices. So these are just matrices whose adjoint is minus itself. Again, in sort of Lie group terms, this is just the Lie algebra of the compact Lie group given by the unitary group. So that's what's going to be a connection for us. So if you like, I mean, again, just a set of 4 matrices with that sort of key property, each one of them. Okay, so once you have the connection, you can form very naturally what we call the connection wave operator that is going to give us our waves. How do we do that? Well, I'm going to tell you first the quick way in which you can do it in geometric terms, and then I'm going to write down what the operator is for you. And I think it is important to take a little bit of time just to look at what the operator actually looks like, so you get a feeling for what is going on. Okay, so this is the sort of highbrow way of defining what the operator is. So if you have this connection A, you have an operator D plus A, and you can take the adjoint, and if you compose the adjoint of that operator with itself, you get the connection wave operator. And this acts on sections of the bundle, which in this case is just simply functions from R4 into Cn. Right, but one can write down a very sort of explicit formula for this, so let me do it for you. And it's actually, I actually do want you to pay attention to this. I do not want to rush through the mathematics in this instance. and it's really not hard at all. So remember, we have been given these sort of 4 matrices, and essentially what this operator is the standard wave operator given by the Minkowski metric, if you like. And then it has this sort of first order term, if you like, in which you consider the first derivatives of the function with respect to the various coordinates, and each one of them is actually being multiplied by the corresponding matrix with the appropriate signs given that we are working in Minkowski space. So there is a sort of second order term, the standard wave operator, and then there is this first order term, which is the one that I guess I would like to pay attention to. And there is some zero order term, which for our purposes is going to be in some sense sort of irrelevant. So that one, if you like, you can actually ignore completely for the purposes of this talk.
It's slightly confusing to me. A is a matrix.
So each one of the A's is a matrix.
And so how can you subtract that from box phi? I'm just confused about the dimensionality.
From box phi there, right. But I mean, keep in fact that the phi takes values in Cn.
I see it.
That's right. So it's a system, basically, right? Where the coefficients of your PDE are actually matrices, and then you apply to a vector value function. That's the section of your vector bundle. Questions like that are great, so please do ask them if you. Okay, everyone happy with that so far? Right. Okay. So so that's going to be the what is going to produce our waves. Next, I need to tell you where we're going to make the measurements. So if you remember at the beginning, I told you we're going to make local measurements of these waves. And we're going to be looking actually at these waves running for a sort of short time, because at some point they're going to be nonlinear, and we only know that these things are going to exist for some kind of fixed time. So I'm going to make something here kind of arbitrary, which is convenient, which is to sort of fix that sort of interval minus 1, 2, so all the action is going to happen in M. And this is going to be, this set W is going to be the set when I'm going to make the observations. So this is essentially just an interval of time 0, 1 times some small ball in R3. So I think I have a picture in a minute. So you can imagine that you have an observer sitting at a fixed point, and then time is running, yeah? And that observer can make measurements in a sort of little neighborhood. So as the time flows, you make measurements, if you like, in this sort of cylinder. So the picture really that I would like you to have in mind is just that one. So you have this small little neighborhood, and then you make your measurements. You sort of move along this sort of red line, this world line, if you like, and you sort of keep measuring. Measuring means, you're being sort of putting sources in a minute, throwing waves, and then measuring how they come back. Okay. And what is the wave equation that we're going to be looking at? So rather than doing the usual thing, which is I first give you the motivation and everything, I first want to tell you what the actual wave equation that I'm going to be looking at is. Yeah? So you focus still on the mathematics, and then I tell you why we're actually looking at this wave equation. So the wave equation is this one. So this is the operator that I have explained to you in the previous 2 slides. And then it has this sort of crucial nonlinear term. Yeah? So remember, and this comes back to the previous question, so phi takes values in Cn, so we can take the norm of that as a vector. So that's a scalar number. So times phi, so the whole sort of equation is essentially in Cn. Yeah? So it has a cubic nonlinearity. Yeah? In some sense, the simplest cubic nonlinearity you can come up with, given that you have vector value objects. And then there is some constant there which is sort of irrelevant as long as it is non-zero. And I'll tell you in a minute what happens if the constant is actually equal to 0. Okay, so that's the nonlinear wave equation. And F is a source. And using this equation, we can define a source-to-solution map. So I think Matti talked about those briefly early in the morning. Maybe I will go through that in some detail in a minute. As I said, the motivation will be coming up very soon. So then let me be a little bit precise about this, what I mean by these measurements, and try to formulate the mathematical problem. So we give a source. The source is small enough, and it's actually supported in this set in which we do the measurements, this set W. And you set things up in such a way that the theory for these nonlinear waves actually apply, and you can solve the forward problem for some fixed time. So you begin with some sort of zero condition for negative time, and you have that source S. So the source to solution map is just simply you give yourself the source, then you solve the wave equation, and then you measure it back on this set where you do the measurements. Okay? Right, and here is the inverse problem. So this is really the question that I would like to address. So can we recover the geometric object, that's the connection, from this source to solution map? Okay. Right, now, the answer is, in principle, not just like that. There's going to be something going on, and this is actually where two things will come into play. The gauges, that were actually mentioned early this morning, and then the fact that we have some causal structure, and the information cannot propagate faster than the speed of light. So we are not going to be able to recover the connection essentially everywhere, but there's going to be some kind of maximal region in which we can expect to do that. So these are the two things I would like to sort of explain to you next, which are very natural. And once we have those, then the question would be, given these two additional sort of bits of insight, then can we actually solve the inverse problem? Okay, so one is the gauge, and I will describe the gauge in detail in a minute, but it's exactly the sort of gauges that were mentioned in the morning. And the other is this thing that we cannot expect, so maybe I'll put the picture right away. We cannot expect to measure things outside this sort of, if you like, causal diamond, to call it in some sense. So maybe the picture is even better than the actual definition of this set D. But this is essentially what you do is each point X has a sort of, past light cone and the inside of the cone, and a future light cone and the forward of the cone. And whenever you have 2 points, you sort of intersect the past cone with the future one, and you do that for all pair of points, and that produces that sort of diamond. And that's the sort of region where you can expect to recover the connection. So you make the measurements on this set W, and then because of its finite speed of propagation, you can expect to recover the connection only in that sort of larger sort of set D. Now, what's the gauge? Okay, this is what I just said. The gauge is the following. So as we were told in the morning, so the gauge is a change of frames. So in this particular instance, I have decided to work with a unitary group. So in the morning, we had SO3 and so on. But I mean, what really matters is that you are working with a nice compact Lie group of matrices. And change of frames means the following, that for every point, you make a choice of a unitary matrix. Yeah? So you can describe that in terms of a map, going from your space M, taking values in the unitary group. And then once you have a gauge, connections change in a natural way. So if you want to define, there's a natural action of this sort of large symmetry group that will take a connection into another one in a natural way. And if you've done just a little bit of physics, you'll see that this is actually the law of transformations for the connections. So you conjugate the connection, this gives you another new one form, and that du is just the differential of this map U, so U inverse du gives you also another one form. So it is actually really just an exercise. Once you write down this gauge, you can go and check that the source to solution map of these two connections is exactly the same. This is really a completely sort of elementary exercise, just looking at the wave equations and checking. There's a natural way of map the solutions of one to the solutions of the other. Okay, so here's the result that I would like to tell you about then. So this is work that I've been doing with Chen, Matti, who is here in the audience, Lauri Oksanen, and maybe I'll say a little bit more about this in a couple of slides. But the result is this, is exactly what the best sort of scenario you could hope for. If you have two connections in R1 plus 3 such that they have the same source to solution map, as long as kappa is different from 0, so you really need this cubic non-linearity, then you can find a gauge. So that means a map from the largest possible set you could hope to find one, from the set D into the unitary group, such that on the set where you do these measurements, the gauge does nothing, because that's a natural thing to happen in that case, such that the two connections are related by this gauge equivalence. Okay, so that's the result that I would like to tell you about. So I can tell you what's coming next. So what's coming next is I will try to motivate now a little bit this cubic wave equation, where does it come from, and actually where we are going, because this is actually part of a kind of long-term project. And then in the last bit of the talk, I'll try to give you some of the main ideas and some sort of flavor of what actually goes, I mean, how do you understand this sort of result? Why do you can actually prove that you can determine the connection in this way? So this, as it often happens in inverse problems, is going to take us to another inverse problem, which is actually quite a fun one, having to do with parallel transport. Okay, everybody happy so far? Okay, so here's the first kind of surprise. So you can ask the same question when kappa is equal to 0. That would be the linear question. And in that case, the problem is actually open. So I don't know if you find that shocking or not, but the non-linear problem is in some sense easier to solve than the linear one. You can even sort of maybe even think that there's some kind of meta principle sort of operating here, that somehow when you go forward, the non-linear problem is harder, but somehow when you go backwards, the non-linearity actually helps you for the inverse problem, which I think is it's an interesting lesson, at least for me.
Open as in you don't know the answer?
Yes.
Open in a mathematical sense?
Open in the sense that in this generality, we don't know if this is true or not. We don't have a proof. Now, if you start putting conditions on the connection, then you might be able to prove things. But you sort of expect that if kappa is equal to 0, that this result will still hold. I would put my money on that, but there's no proof. Okay, so the motivation actually comes from an important set of equations in physics called the Yang-Mills-Higgs equations. So I'll run quickly through them, and I'll try to sort of explain why we were looking at this wave equation. But essentially, to sort of anticipate, the phi is kind of playing the role of the Higgs field, basically. So this is the sort of equation that kind of commands the behavior of the Higgs field. So the Yang-Mills-Higgs equations are actually is a couple set of equations that involve two geometric objects, a connection, which I told you what it is, and a field, phi, which is actually, in this case, is actually matrix value. So I have sort of given you a simplified model in the previous thing, but and it looks like this. So there are various objects here, which I could run through quickly, if you like, but the connections have the kind of important physical quantity, which is the curvature, which is actually the field strength, yeah? So if the connection was actually just a 1-by-1 matrix, you would have just a magnetic potential, and the differential of that would be the curvature, which is just a magnetic field. So here's exactly the same thing, but in this sort of non-abelian setting, where you're working with sort of matrices rather than 1-by-1 objects. So F is the curvature, and the curvature, well, can be defined in a very sort of explicit way, which I don't want to do at the moment. And these are the various sort of operators that pop up. There are sort of various derivatives associated with the connection. This sort of big capital dA is defined in that form, with that sort of bracket of matrices, essentially. And then there's some potential there, which depends on the norm of the Higgs field phi. And this is somehow the potential that will give the non-linearity in the equation. So, in fact, the choice of this potential, which is in some sense the simplest one you could possibly pick, which is a quadratic potential, will actually produce a non-linearity exactly of the type that I showed to you before. And now, maybe I should say, because I learned this from Matti yesterday, this is actually a very common choice of potential. So there's a minor variation of this, which is the Mexican hat potential, which is exactly the one that the physicists use to sort of explain the Higgs mechanism, which is the way actually the Higgs field gives mass to the various particles that need to have mass to fit into the standard model. So the equation then that I show you for which we solve this inverse problem is actually the equation that you get when you look at these couple equations, and then you just kicked out the first one, yeah, and you essentially measuring the Higgs field. So I told you before that the person making the measurements was very clever, so I was actually able to sort of fabricate sources of Higgs fields and then measuring back, something that is probably not something that we can do in real life. But that is exactly that equation. And really the reason why we've been actually looking at that particular problem is because our long-term goal is actually to solve the same sort of circle of questions, but now for the full Young-Mills-Higgs system, which I think is exactly what I put there. And so that's really what that equation comes from and the motivation. And perhaps maybe I should just say one thing, sort of a little bit of an aside. I don't know, some of you probably have heard, I mean, if you're in the inverse problems community, you do know that Slava Kurilev passed away recently. This project that we are now doing with Matti, with Chen, and with Larry, actually began with Slava on board, and so his influence actually and his thoughts were very important for us to sort of start kind of shaping this and make the project what it is today. Okay, so I'd like to tell you then a little bit about the ideas. So I already told you, so really the nonlinearity of these equations is actually helping you. And the proof does exploit a kind of recent philosophy that has emerged, I guess, in the inverse problems group in the last maybe 4 or 5 years, maybe a little bit more, in which the nonlinearity actually help you in the sense that they produce sort of nonlinear interaction of waves, and this actually give you a much richer kind of dynamics, if you like. And this is what I will try to sort of explain. In the context of the Einstein equations, or the Einstein-Maxwell equations, there's been a wonderful series of papers in the last 4 years by various people, some of them here in the audience, in various sort of combinations. And I think there are some problems also using this sort of idea in elasticity, right, Martin? Maybe in which you're involved as well. So it's a sort of fairly active area at the moment, based in this very beautiful idea that using this nonlinear interaction of waves makes the inverse problem in some sense doable, even when you cannot do the linear one. So what we are doing really here, or what I am actually telling you about, is that we are keeping space-time fixed, and we are actually going after the connection that, if you remember when I show you to ask you to pay attention at the actual sort of operator, the connection appears in the first order term. So in some sense, it's a kind of weaker thing, and probably less visible from the data if you compare with a metric, that somehow you can think of the metric as appearing as the leading term. Yeah. Okay. So the other thing in which this is a little bit different from the previous literature is that we consider the sort of interaction of 3 waves, while all the previous literature was actually considered the interaction of 4 waves. Essentially because, and this will explain, I guess, some of the pictures that will come in a minute, the sort of idea of this is that you will launch, let's say, so keep in mind that you have this freedom for actually producing these sources. So you can put sort of, let's say, point sources. You can think that you can put, let's say, 4 of them, and you launch, let's say, spherical waves, yeah, along light-like geodesics. This will, if you launch them right, will eventually meet at some point, and because of the dimensions, if you're launching 4, essentially in a generic situation, they will intersect at a point. And this point will create a sort of a new sort of artificial point source that will propagate and possibly return to this set W. Now we're dealing here with 3 waves. So that changes the game a little bit, because what we're actually going to create is not just a point source, but a sort of artificial filament. And this artificial filament is going to sort of become the sources of the waves. And from a technical point of view, dealing with these sort of three waves was a bit of a challenge. So in mathematical terms, this is what we do. You write your source as a sort of combination of three sources. So these are the three waves. And as I said, so these are singular waves, if you like, have wavefront sets, and they propagate along the geodesics. And we choose those in a very careful, clever way. So remember, you are the person making, or we are the people making the measurements, so we have the freedom to pick the source that we want. And you linearize 3 times, so you differentiate that nonlinear wave equation with respect to this sort of expansion 3 times. And if you do that, and you actually compute, you get an equation that looks like this. So this is the wave connection operator. This is the triple derivative of the function phi. And then you have this sort of nonlinear term with this sort of cubic nonlinear term. This is just a real part, because remember, we are working on sort of Cn, so we have a Hermitian in the product. So I eventually have to take real parts here. That's what pops up. Where each one of these sort of VI satisfies a regular linear wave equation with the connection A. That's right. So you get that equation if you choose a suitable kappa, which is 1/2, or I do not remember. Otherwise, there is a kappa there.
Okay, so is kappa focusing or defocusing?
It doesn't matter. It doesn't make any difference.
So if you're choosing 1/2, it's either 1/2 or -1. One focusing, one defocusing. One amplifies the nonlinear effect, one.
Yeah, but I don't think it's going to matter much for the proof we do. Yeah, this is for a kappa, but I guess what I'm trying to say is it doesn't matter which kappa you choose, the proof that we have will actually work. Yeah, so, but that equation I have written with a specific kappa, because I didn't want to have kappa there. Yeah. Okay, so the nonlinear interaction of the waves is actually given by that sort of right-hand side. And this is somehow where the sort of, essentially, the tool of microlocal analysis come into play. So there's been a machinery that has been developed to deal with this sort of interactions. And it's actually a wonderful machinery, in some sense sort of fairly classical. And this is somehow what we do. So we analyze in a microlocal sense that sort of interaction of those 3 waves. And of course, you want to make the waves come back to the measurement set W, right? So you have to actually prove that you can produce sources so that when you have this nonlinear interaction, these waves actually do come back to this set W, and they come back in abundance in some sense. So there's a lot of things that one has to actually prove here. But the interesting thing is that somehow the information that you actually get from this coming back and for using this sort of microlocal sort of analysis is what is a new sort of geometric object. What you actually recover from these sort of measurements is what we call the broken non-abelian X-ray transform, which I would like to tell you in a minute in the last bit of the talk. So this is a kind of a schematic picture. So what happens in the proof is that you fix the points x, y, and z. You fix that direction psi1 and the exiting direction eta. And then you show that you can actually choose psi2 and psi1 so that eta is in the linear span of these 3. And then that's how you choose these points x1 and x3, so that when you get to the point of interaction, you have this sort of artificial filament that I told you about will emit in the direction of this point, this vector eta. And then you get back to your set W. And this is somehow, this takes some effort. Okay, so there's quite a lot of tech that is available for this, and this is what we use. And I think, so next, I'd like to show you a movie of these waves and how they interact and they produce this artificial filament. So the 3 waves come in, there's some nonlinear interaction, and then the filament emits this sort of outgoing wave. Yeah? So there I run it backwards. I stop it a little bit, so that's the moment of creation of the filament, and then shoots off again, and goes back.
So the waves you send in had an epsilon in front. Is that right? So do I recall correctly from the superimposition of 3 waves?
Yes, yeah, yeah. Yeah. But I guess the picture that I'm showing you are the wavefront sets after you linearize and you differentiate it.
But still, before linearization,
Yes, yeah.
There's an epsilon in front, so
Yeah.
it's small somehow.
Yeah.
And then the nonlinearity is cubic, so somehow the effect you're creating is epsilon cubed, is that correct?
Yeah, in some sense, yes.
Somehow lower.
Yeah. Okay, it should stop. Doesn't want to advance now. Okay, so there we go. So I think I'll finish the last few minutes telling you a little bit about this new geometric inverse problems that pops up with this broken non-abelian X-ray. So once you do all this analysis and the sort of interactions of these waves and so on, what you actually recover is this thing that we call the broken scattering data for the connection. And this is where the parallel transport comes into play. So what is this? Well, the picture that one has is something like this. So you move along a light ray geodesic up to the point Y. This point Y is in this sort of set D, this sort of maximal diamond. And then you come back to the place where you make the measurements to the point Z. And what you actually recover, what you know, is the parallel transport starting from the point X, going all the way to Y, and then continue there to the point Z. So you can do a parallel transport along any sort of piecewise smooth path. I will tell you in a minute what the parallel transport was, because I don't think it was actually defined in the morning. So I will tell you exactly what it is so you know. So let me call that SA this sort of parallel transport from X to Y and then from Y to Z. And this is the way the parallel transport is defined. It's really a very, very simple idea. So remember, we have this matrix A, we have in fact 4 matrices, right? But you have a curve, and the curve has a velocity vector. So you can actually, that one form can be evaluated along the curve, and that produces a matrix that depends just on T. And then you have a matrix that depends on D, and then you solve the fundamental solution of your ODE system, something that we teach our sort of undergraduates. Yeah? And the parallel transport is just simply, let's say you begin with the identity at the point X, you solve that equation, and then with that point that you finish, you go all the way, you restart with that initial condition, and then you continue all the way to Z, and then at the end, the parallel transport is just that unitary matrix that pops up at the end. So essentially what we recover is actually this. Yeah? And now we have this other geometric inverse problem, which is a kind of ODE inverse problem in which we need to recover the connection from this broken non-abelian X-ray. The reason why this is called broken non-abelian X-ray is because if you were to do this with just 1 by 1, and you didn't have broken rays, you will have just straight lines in the plane, you will get the classical X-ray transform. Yeah? But now, since you're dealing with matrices, and this is a non-abelian setting, all these sort of non-abelian X-ray questions are actually pretty hard. And the geometric problem that we actually solved is this one. So if you have 2 connections that have the same broken non-abelian X-ray transform, then those connections are actually related by a gauge equivalence. So there is a gauge that is defined in this maximal diamond, taking values in the unitary group, such that you get into that. Yeah? So if you like the proof has sort of 2 components. There is this sort of nonlinear interaction of waves that you analyze with macrolocal analysis by looking at the wavefront sets and Coulomb singularities and so on. And then once you get into this problem, you get into a purely geometric problem, which of course I like very much. Okay, so I think I'm going to sort of apologize just before I show you the next 2 slides. So I'm going to give a proof of something. Do I have 10 minutes? So I'm going to prove something. So I'm not going to prove that theorem, but I'm going to prove you a simplified version of that it will give you, it's the simplest non-trivial case that I can think of that will give you the idea of why actually you can solve this. And it's elementary, so just bear with me. Okay, so the simplified question is just a question in the plane. So you have two connections in the plane. Assume they have compact support, so they are very nice. Outside some set, they are all 0. And then you do the following very simple-minded thing. You consider the parallel transport just along broken horizontal and vertical lines. So you come from minus infinity, you stop at a point x, and then you shoot off from x to plus infinity. So you call that the scattering data of the connection, and then you ask yourself the following very simple question. If you have two connections with the same scattering data, are they gauge equivalent? How do you go about proving that? Yeah. Okay, and it's all about gauges in some sense, right? So gauges gives you the sort of freedom of moving things around. So for example, the proof of this consists in you being very clever and selecting the right choice from the start. So then the problem that you have to solve actually ends up being a very simple ODE problem. So what you do is the following simple thing. You consider the following gauge, in which you essentially go up using one of the connections, parallel transport going up with one connection, solving an ODE with A, but then you come down with B. That gives you a function of x, and that function of x is a unitary map, because the solutions of these things are unitary because the matrix A is skew Hermitian. Okay, so that gives you A, and then you construct a new connection from A by the gauge rule that I told you about, and then as you go away, and it's an exercise to check that the second component, so we are working in R2, so the connection now is just two matrices, A1 and A2. And with that choice of gauge, you can check that the second components of the two connections are the same. So you have already arranged things so that you can kick out half of the issue and focus on the other two components. Great. So the next thing that you observe, because I told you about curvature, so it's a proof using curvature, is that, again, if you have this information that the scattering data is the same, and you know that these two second components are the same, you go away, and it will take you maybe 10 minutes to see that what actually happens is that the parallel transport along a small square like this one is actually the same for both connections. But you can recover curvature from parallel transport. So if I let this square go to 0, and this is the last slide, then what I end up actually proving is that the two connections have the same curvature. So I now have two connections with the same curvature and with the two sort of same second components. Essentially, you write down now what the curvature is, and now I can tell you what the curvature is. So here is a formula for the curvature. This is what you will see in the physics books, actually. You write down what it is, and then you use the fact that the second components of the connections are the same, and you write the equation now for the first components using that they have the same curvature, and you get an ODE essentially with 0 initial conditions, so it has to be 0. And then you get that A1 equals P1. So the proof in the general case is more complicated than that in the Minkowski's case, but the kind of underlying idea is that. And there is then here a kind of second lesson is that the fact that this is a broken X-ray is helping you a lot. So the problem where you don't have, when the geodesics are not broken, yeah? So even this problem that I just told you about, of two connections in the plane, if you just look at the parallel transport along straight lines, you can ask the same question. And the answer to that question is actually no and positive, but it's a really non-trivial, very difficult theorem. So the broken X-ray is actually helping you. So in some sense, there are two kind of beautiful things going on with this cubic wave equation. There's a sort of nonlinear interactions of waves that would take you to this broken X-ray transform, and then the fact that you can solve this broken X-ray question so nicely, thanks precisely to the fact that you're breaking